All right, we have p of x, which is a third degree polynomial defined up here at the top. 1/4 x cubed minus 2x. And we're going to talk about the derivative of p of x at a few points using the limit definition of the derivative. So first part, let's graph it, right? Because the algebra should always make sense with the graph. So there's my x-axis, there's my y-axis. And if we were to graph p of x, note that there's an x in both terms. So this actually factors one of my zeros of this polynomial is x. And then you have this quadratic, which you can then solve for those two x values. But I'll skip that because we should already be experts at that. You get a 0 there. You also pick up another 0 at approximately minus 2.8. So somewhere right there. And then your third 0 of this cubic is the symmetric 2.8, about positive 2.8. So about there, right? It's also cubic with a positive leading coefficient. We know that it's going to look like this. Right. Okay, so that's the graph of p of x. Now, number two, find the instantaneous rate of change, or another way to say that, the slope of the tangent lines, or another way to say that is the derivative. All of these things are the same thing. Derivative, instantaneous rate of change, slope of the tangent line. We want to find these of p of x at the points x is equal to 2. So let's go ahead and locate that. I'm looking for a tangent line right there. And I'm also looking for a tangent line. Oh, sorry, that's negative 2. Where's positive 2? Over here. And at minus 1. It's right there. Okay, so let's do this. The value of the derivative, oh, it's not called f, it's called p. P prime of x. Right, the value of the derivative is the slope of the tangent line. It is the instantaneous rate of change. So we want to find the limit as h goes to 0 of p. So let's write down the general definition first. So if I'm evaluating a derivative at a point x naught, then it would be x naught plus h minus p at x naught over h. Right, this right here is the slope of the secant line. And then this limit turns those secant lines into a tangent line, right? I collapse an interval around x naught. This is our definition of the derivative. Let's chase the algebra. And then at the very end, we'll take the limit, which is the calculus. So what is my polynomial, my p of x at x naught plus h? That'd be 1/4 x naught plus h cubed minus 2 x naught plus h. Right, that is my function evaluated at x naught plus h. I'll then subtract from this the function at x naught. So I'll subtract from this 1/4 x naught cubed minus 2 x naught. Remember, wrap that in parentheses because you want to subtract off the whole function at x naught. And we'll divide this by h. Now, in another video, I'll do a derivative as a function. Here, we want to evaluate the derivative at a specific point. So let's let x naught be 2. Limit as h goes to 0, 1/4. My x naught is 2. All right. Limit h is going to go to 0. Let's figure out what one of these 2 plus h's is. So we'll leave one alone. The other two will combine as 4 plus 4h plus 4. I have a minus 4 minus a 2h. This term right here, 2 cubed will give me an 8. 8 divided by 4 is a 2. So I'm subtracting a 2. And this minus sign, that minus sign means that I'm going to add a 4. Limit as h goes to 0. We have that 1/4 being multiplied by 2 plus h cubed. Let's figure out what 2 plus h cubed is. That's going to be 8 plus 8h plus 8. Oh, wait, that can't be right. Oops. Yep, I see a mistake. That 4 is supposed to be an h squared. Right, if I did this right, 2 times 2 gives me that 4. I've got two h's, and then I got h squared. All right, so this isn't an 8, but rather a 2h squared. Then we have a plus 4h plus 4h squared plus an h cubed. Now we can go ahead and cancel as we go. We got this minus 4, we got the plus 4. So what do we have left? We have a minus 2h and a minus 2. All right, limit as h goes to 0, 1/4. In fact, let's go ahead and bring that 1/4 through. So what do we have? We have 2 plus 2h plus 1/2 h squared plus h squared plus 1/4 h cubed minus 2h minus 2 all over h. And what can we combine? I've got a plus 2, a minus 2, a plus 2h, minus 2h. And I think we're done. So I've got a 1/2 h squared and an h squared. So I've got 3/2 h squared. How many h's do I have? Just one of them. So plus the h. And then how many h cubes do I have? 1/4 h cubed. Now I can take an h away from my numerator. That leaves me with 3/2 h plus 1 plus 1/4 h squared. Now I see that cancellation. This gives me limit as h goes to 0, 3/2 h plus 1 plus 1/4 h squared, which gives me just that 1. Cool, so let's go back up to our graph. We just told ourselves that the instantaneous rate of change of this function p of x at the point 2 was 1. And it kind of looks like that from our picture, right? The tangent line, the line whose slope is the instantaneous rate of change of p of x at this point 2, has a slope of 1. So at that instant in time, at that single x value, the function p of x is changing at a rate of 1 unit per unit change in your x. Let's do the same thing for the other point. X is now equal to minus 1. So we'll look at the value of the derivative at minus 1. That is the limit as h goes to 0 of the function at minus 1 plus h minus the function at minus 1 over h, right? The limit of the difference quotients, the limit of the slopes of secant lines. So a lot of this is going to be repetitive because we're dealing with the same function. We're just changing the point. This is going to be 1/4 minus 1. In fact, instead of writing minus 1 plus h, why not write it as h minus 1? It's the same thing, and it's easier. Cubed minus 2h h minus 1, right? This right here is my function at minus 1 plus h. Then we have minus the function at minus 1. So that is 1/4 minus 1 cubed minus 2 times minus 1 over h. So now what do we have? We have that 1/4 times h minus 1, h squared minus 2h plus 1 minus 2h plus 2. And then the minus 1 cubed is going to give me a minus 1. So we have a plus 1/4 and a plus 2. Oh, nope. See my mistake. That minus and that minus leaves this term as a plus 2. And then this minus is going to subtract the 2. So we actually do have a minus 2 there. Minus 2. Right, the hardest part of calculus is the algebra. What do we have here? 1/4. If I send this h through, I get h cubed minus 2h squared plus h. And if I send this minus 1 through, I get a minus h squared plus a 2h minus a 1. Minus 2h. Let's go ahead and cancel those plus 2's minus 2's. So we have that 1/4 there. All on top of h. Right, and always copy down that limit sign until you're ready to take it. Let's send the 1/4 through. So we have 1/4 h cubed minus 1/2 h squared plus 1/4 h minus 1/4 h squared plus 1/2 h minus 1/4 minus 2h plus 1/4. And you could have simplified your parentheses before you sent the 1/4 through. That might have been a little bit easier. What do we have? How many h cubes? 1/4 h cubed. Let's underline them as we go to make sure that we don't miss any. How many h squareds do we have? We have minus 1/2 of them, then minus a quarter. And that's it. So what is that? That's minus 2, minus 3, minus 3/4. All right, how many h's do we have? Plus 1/4, plus a half, so plus 3/4. And then minus 2. What is that? Minus 2 plus 3/4. That gives me minus 5/4. So that's how many h's we have. Minus 5/4 h. And we don't have any constants because minus 1/4 plus 1/4. Okay. We still have the division by h, which we can go ahead and cancel. If I pull an h away from my numerator and cancel it with the one in my denominator, I have 1/4 h squared minus 3/4 h minus 5/4. And now I can directly substitute. I can send h to 0. I get minus 5/4. So let's go back up to our picture. We just told ourselves that the instantaneous rate of change of this function at the point minus 1 is minus 5/4. And that makes sense according to our picture, right? It looks like it's going to have a negative slope right there. And the slope of that tangent line right there is minus 5/4.